We're going to talk about target 3, using the kinetic molecular theory to describe the behavior of gases and how gas particles exert pressure. We're also going to talk about conversion in gas, going from ATM to millimeters mercury to PSI, and with temperature, going between Celsius and Kelvin. Why do we want to talk about gases? Well, let's think about Earth. The mass of the Earth is 5.97 times 10 to the 24th kilograms. That's really massive. But what is Earth? What are the components of Earth? Well, the Earth's atmosphere alone is 5.1 times 10 to the 18th kilograms. That's only 0.0000854% of the Earth's total mass, but what is all of that atmosphere made of? Gas. All of that atmosphere is made of gas. That is that many zeros, kilograms of gas. And the atmosphere goes up to 300 miles above the surface. So what is a gas? It's a state of matter that we talked about first semester, solid, liquid, or gas. The gas, if you want to look back at your page on 19, there's no definite shape. It will take the shape of whatever container it's in. There's no definite volume. It'll take the volume of whatever container it's in. It is fully compressible. The particles spread out to be able to get to all parts of the container like you see in the picture here. And the particles are moving very fast. You can double check your work from the top of this page. That solid has a definite shape, definite volume, it is not compressible, and it's very packed and rigid. As you can see on the left here, that's your solid. Then liquid, the shape, it's a definite it's a variable shape because it goes depending on what the container is. Beaker versus graduated cylinder versus bottle. The volume is definite. When you have 100 milliliters in a bottle and you pour that water into a, say, beaker, you're still going to have 100 milliliters. And then if you pour it into a graduated cylinder, you're still going to have 100 milliliters. So there's definitely a definite volume. It is not compressible, and the motion is close contact and free to flow. As you see here, this one was the one that was showing you liquid. And then finally on the right, gas, it's a variable shape. It takes the shape of the container. It's a variable volume. It'll take the shape or the volume of the container. It is compressible and it's very fast. So here is a video for you to listen. Or we're not going to watch it. That's okay. We'll move on. The kinetic molecular theory of gases. Gas particles are so small their volumes can be ignored. They have a mass but almost no volume. Gas particles move rapidly and randomly. There is no set pattern as you saw from the atoms in motion activity. The collisions with the walls of the container cause the pressure on the container, and that hopefully you saw in the atoms in motion, that when you paused it as soon as it hit the side of the container, you saw that the pressure increased, and so that it's the collisions against the walls and each other that will make the pressure increase. The kinetic energy of gas particles is directly proportional to their temperature. So also hopefully you saw in the atoms in motion, as you increased the temperature, you actually had an increase in the pressure. You'll be hearing the term STP. What does STP mean? Gases are often measured using STP. It stands for standard temperature and pressure. The conditions for STP, well, standard temperature is going to be 0 degrees Celsius, which is the same thing as 273 Kelvin. And standard pressure is going to be 1 atm atmospheric, or 760 mmHg, which is millimeters mercury. Pressure. There are 3 units that we're going to talk about. What is pressure, though? Pressure is the force exerted on a given area. The units: atmosphere, atm, millimeters mercury, that's mmHg, and finally psi, which is pounds per square inch. We will give you these conversion factors. 1 atm equals 760 millimeters mercury, which equals 14.7 psi. So 1 atm equals 14.7 psi. 760 millimeters mercury equals 14.7 psi. Now, in the space right beneath this, before we get to temperature, I want you to do a couple of practice problems. First, let's do 0.75 atm, and we want to convert it to millimeters mercury. Remember those T-charts from stoichiometry? We're going to go back to them. So you have 0.75 atm on the top, and I want to convert it to millimeters mercury. And so you can see here that this is what I want to get to. I want to get to millimeters mercury, and that's really, do that smaller. And so what I'll do is I'll put 0.785 atm on the top, 1 atm on the bottom, and then I can see that I can cross off my atm. And then we know from the previous slide, 1 atm equals 760 millimeters mercury. And so that will equal 570 millimeters mercury. The next one, I want to convert 1420 millimeters mercury to atm. So you're going to want to start with mercury on the top left, and you want to put atm in the top right. So let's see what that setup looks like. And so you can see 1420 millimeters mercury in the numerator on the left, and then on the bottom right, I want to get rid of millimeters mercury to cross it out, and so I know that 1 atm equals 760 millimeters mercury, so you're going to do 1420 divided by 760, which is 1.87 atm. Next, 5 atm to psi. I'm going to start with 5 atm. My setup looks like this. And then you will put 1 atm on the bottom right so that you can cross it off. Cancel it out. And then psi on the top. And that equals 73.5 psi. Finally, the last one, 34 psi to millimeters mercury. You're going to start with psi on the top left. And then we know that 14.7 psi equals 760 millimeters mercury. And when you do 34 times 760, and then divide by 14.7. And you should get 1,757.82 millimeters of mercury. Next, we're going to do temperature. Temperature is very simple. It's the measure of the kinetic energy of an object. We've talked about this with specific heat. Excuse me. And we're only going to be converting between Celsius and Kelvin. And it's a very simple conversion, just to let you know the coldest temperature there is, that with absolutely no energy at all, is at 0 Kelvin. That's absolute 0. Conversion factors is that when you want to calculate for Kelvin, it's Kelvin equals whatever the temperature in Celsius plus 273. And if you want to convert from Celsius, whatever you're going to do K minus 273. So right underneath, just like we did before, let's practice it. So I want to convert 5K to degrees Celsius. So you're just going to do 5K minus 273, and that's what you'll get for your equals negative 268 degrees Celsius. Now if I want to convert Celsius to Kelvin, you're going to do the opposite. You're going to do negative 10 plus 273, which will then equal 63 Kelvin. Finally, your volume. Volume is the amount of space that an object occupies. Think of it in terms of like a beaker, graduated cylinder. It's a space in which 100 milliliters would occupy. Conversion, we did this also in the fall semester. Our typical units are liters. You'll also see milliliters. And the conversion factor is 1 liter equals 1,000 milliliters. So underneath this spot, we have a couple of practice problems. 5.5 liters to milliliters. Again, with the T-chart, you'll start with 5.5 liters in the top left. We know that 1 liter equals 1,000 milliliters, and so 5.5 times 1,000. And then if we want to convert 264 milliliters to liters, do the T-chart, 263 milliliters in the top left, 1 liter equals 1,000 milliliters, and then you divide 263 by 1,000, and so you get 0.264 liters. That's it.